done them again here. Okay, so I won't waste much of time talking about such things. I want to talk about the things that were especially new to you guys. Okay, so from set theory, we of course did see that we still met the intersection and the union, right? We got to meet this again at this level. So basically, I want you to use the approach of shading. I've been trying to emphasize on the part of shading if you want to understand sets, especially in a case where they ask you to describe the shaded region, they ask you to simplify. Basically, shading is the best way to make your life easier. So, in a case where you have A and B, basically, generally, what you may talk about is a case where you are talking about A and B with an intersection part. Okay? So, in such a case, you talk about the intersection to be that region in between. Okay, so apart from that, which is something that looks so simple to you, there may be some cases where you have sets that may not share an intersection, such sets. Then they ask you to shade A intersection B, or they just ask you to find A intersection B. Usually the question that they like asking is they'll ask you to simplify. So what is A intersection B in this case? Where our sets are like that. What would you say? So our A intersection B is what? Is basically going to be considered an empty set because it's an empty set because we don't have any elements that are part of both A and what? A and B. They don't share an intersection. So I'm sure we've already talked about this. We already know what it's all about. Now, in a case where we talk about the union, it's very important for us to understand that it basically tells us to combine all these elements together. So by combining, we mean what you're going to have is you shade all the elements in A with B, you get to combine them together in a single set. That is what we call the union of A and B. Okay, that's very simple. I'm sure there are no questions on that. Now things begin to advance bit by bit. I'm trying to exhaust this topic in 30 minutes. I'm trying to attempt to exhaust all the important concepts within 30 minutes. So, apart from that, we also came to meet the complement, right? We came to meet the complement again. But in this case, we met it in a different form, where it is A minus B, for example. What would you say? What does it mean? Most of the people face challenges interpreting what it means when you say A minus B. So basically, A minus B means A without what? A without B. So what is the easiest interpretation of that? So if you say A without B, in a case where you have sets like that, so I'm trying to use the approach of shading to help you understand better. So in a case where you have two sets with an intersection, and then you say A without B, it means we're interested in A, but what are we doing? We're removing that part of B. So generally, this is what we are calling our A, right? That is the entire region of A. But when we say minus B, we are saying without B. So every region that is part of A and part of B, we are going to exclude it from the shaded region. So this part is going to be excluded. Why are we excluding it? Because it is part of what? It is part of B. Because we are interested in A without B. So what turns out to be our solution is basically just shading this region. Okay, we exclude the part that is part of B. That is what it means when you say A minus B. So basically, how do you get to simplify it then? You'd want to think about it in a different way, where you say, okay, well, let's assume we didn't basically have A minus B, and then we're asked to describe the shaded region. How would you approach it? How would you look at the shaded region? So first of all, you're going to think about it in this way. You're going to note that the shaded region is part of A, of course. Then the question is it part of B? I'm sure it's not. You would agree with me that it's not. So it's not part of B. If it's not part of B entirely, then it's part of what? Its complement. So what we're trying to say is the shaded region there is part of A, and it is also part of B complement, meaning that it is also outside B. So we can therefore say that A minus B is the same as A intersection B complement. The shaded region is part of A and also outside B. That is the interpretation there. Okay. Any questions? Now let's try to look at a practice example, which basically may not require us to. Yes, is a question? Do we have a question? Oh, sorry, you are late. Yeah. So everyone can see the work that I'm doing? Is that the case with everyone? Okay, let me stop presenting, then I restart again for the sake of those who can see. I'm sure you are now able to see. Can you see now? Okay, are we ready to go? You can't see the screen. Can you see now? Alright. So, I'm sure we've understood now for the part of A minus B, right? Okay. So now I want to use a smart way. I want you to approach it. Let's try to think of a case where we have our union, right? Let's say our union is made up of elements from 0 all the way up to, let's say, let me make it simple, just up to 6. Then you have a set A, right? Then A is made up of 2, 4, and 6. So now, U minus M. What do you think about it? When we think about U minus A, from the interpretation we said it's going to be U without what? Without A. Are we together? So that means that we're going to look at the universal set, which is our U in this case. We're going to look at it and remove all the elements that are part of it, because we are saying it is the universal set minus what? Minus A. So you do even want to show it in this way. You can't see the screen. Okay. Just a minute. Anything now? Can you see? Okay, let me leave in a just just give me 20 seconds. Just give me 30 seconds. Let me just leave and join again. You got to solve the issue. Are you following Mr. Chacha? Is that visible? Okay, so I would say when you're looking at u minus a, the universal set without a, it means that we need to exclude the members that are part of a from the universal set. So I was trying to show that by subtracting. So what we have minus the other set 2, 4 and 2, 4 and 6, right? So let me just write it down. Minus 2, 4 and 6. So I've just like substituted what we have on our left. So now the interpretation here is you need to exclude these elements from the universal set 2, 4 and 6. So remove 2, 4 and 6. What are we going to have? So what is going to remain is we're going to remain with 0, 1 and 5. Okay, so now the question is, what about if we talked about a complement? What elements are outside A? So I think there was one element that was left to 3. Okay, thank you. I've seen it. Then for A complement, what are we going to have? You can only see the logo. Is there anyone who is able to see? Are we able to see? Okay, I don't. So what you can do, just leave and join again. You'll be able to see. So for A complement, we basically talk about the elements outside our A, right? So we can talk about outside our A. We have 2, 4 and 6. So what is basically outside that set? So a complement of a set, basically, guys, what you need to know is you are interested in the elements outside the given set, but should be what? Should be within the universal set. So in this case, the elements outside A are the other elements that are not in this set, but within the universal. So what are those elements? So we have 0, 1, 3, 5, right? So here what we can notice, we can see basically that our A complement is equivalent to the universal set minus what? Minus A. So in other terms, what you guys have to know is the universal set minus any set is basically the complement of that set. Are we together? So if you have universal minus A, this is the same as what? A complement. Are we together? So now we would want to simplify it first of all. Union we're going by what we had come up with. We said A minus B is equivalent to what? A intersection B complement, right? That's what we said. Not so. So now, if you say U minus A, we are saying the inverse set intersection A complement. That's what we are saying. Now, when you look at this, what is the intersection of a set and the inverse set? So I want you to understand it in terms of shading. So this is your inverse set. Then you have a certain set inside, which is A. So when you think about the intersection, U intersection A, what can you say? So the basic concept is when you're talking about the intersection, you're trying to talk about the common elements, right? So we need to realize that any given set, being B A itself or its complement, they are all within the universal set. So when you talk about the intersection, you're supposed to shade. So I'll shade the inverse. The inverse set is in the entire set, right? Then I can use a different color to shade my A, maybe red. So now, who understands what the intersection is? The intersection is going to be a region where these lines are meeting from, right? A with the universal set. So what can you note there? You can basically note that it's basically the set A itself, not so. That is the point of intersection. Are we together? So any set being intersected with the inverse set is going to be that set itself. So even when we talk about the complement of a set, it is still going to be a complement, because a complement is within complement itself and also within the inverse set. I hope that's okay there. Let's get to move. If we don't have any questions, we can move. Hello? Can we move? Okay, let's try to review the set laws before we get to move to set interval notation. Okay, so I'm sure we know what set laws are. I'm going to talk about the most important ones. Of course, the commutative laws are simple things. By commutative, we are talking about the case where you're intersecting a set, two sets. So you find that whether you start with B intersection A, they are one and the same, right? We call these commutative laws. So even though union, they are applicable, whether you start with B union A, these are going to be one and the same. Are we together? So these are called commutative laws. A intersection B is the same as B intersection A. So it doesn't matter what you get to start with. Any questions there? There are no questions. Thank you. So as we get to proceed and get to move, there are some more important laws that we can talk about. Commutative, for example, commutative is not very important, but De Morgan's is something that you're going to be assessed on most of the times. So what are these De Morgan's laws that we're talking about? So De Morgan's laws basically gets to apply to a case where you get to talk about the intersection of two sets, then the complement of it, and also the union. So in a case where you have the intersection of two sets in brackets, then you also have the union of two sets in brackets. Then you get to have a complement outside. So you're trying to study the trend there. So it's basically been proven that A intersection B complement is the same as what? A complement union B complement. Then the other case, it's A complement intersection what? B complement. Do we have any questions there? Do we have questions? I'm getting you. I'm getting you, madam. Yes, what's your question? Hello, am I the only one who's not getting her? Okay, so these are the two De Morgan's laws that we're talking about. So now, I'm sure we are able to remember them, right? So now, I'm sure you've seen questions where they ask you to confirm, they ask you to prove, and whatnot. So, how do you get to, first of all, prove these without given any sets? In a case where you're not given any sets, how do you get to prove them? So I basically like the approach of shading, because it basically gives us an understanding of what we are talking about. So I'll start with my left hand side. So let me do this. We have A intersection B, then we have complement of it, right? Then this should be equal to A complement union B complement. So guys, when you're talking about A intersection B, what does it mean? You're talking about the intersection of two sets, then outside of it. So basically, to start with, you have two sets A and B, right? That's what you have. Then intersection means that part there. But then, is that the region that we're interested in? So I can just show down that this is our A intersection B, not so. Then I can say, therefore, my A intersection B complement is going to be the region other than the shaded region on top there. Do we understand that, guys? So you are going to shade now the region outside what you shaded on top. That is what is going to be the complement of the set, because that's what we said. When you have a set in the inverse set, for example A, if A is that, then the A complement is going to be the region other than that, but within the inverse set. So it would be something outside A itself. That's what we are trying to say there. Does that make sense? So with an understanding of what a complement is, we can now show the complement of A intersection B there. Okay, so just guys, be patient. We're going to review all the concepts on set theory, so be patient even as we get to proceed. As we get to the ones that you may be facing challenges with. So if this is okay, just stay. You get to meet what you need. So now A intersection B complement, we are saying it's a region outside the shaded region on top there, because what we've shaded on top is A intersection B. So now its complement means the region outside that. So it's going to be this region. So the only region that I'm excluding is what? The middle part. Are we together? So the only region that I've excluded is A intersection B, and that is basically our A intersection B complement. So now for the other part where we have A complement union B complement, I'm going to start first of all with my A complement. So you can note that your A complement, basically, we are looking at it in a case where you have two sets already, A and B, right? Kindly mute your mic. Mute your mic, we're getting you. Okay, thank you. So let's say you have two sets A and B, like that. So we are trying to first of all show our A complement. So we do understand that our A complement is going to be the set outside our A, right? So that is what we're going to have there. The entire region outside our A is going to be what? Our A complement. Any questions? We can also then talk about B complement. B complement on the other part is going to include the region outside what? It's going to include the region outside your B. So if you have your A there and your B, and then you get to shade the region outside B, that is going to be our B complement. So this is our B complement. So now, what have we been taught, guys? We are trying to find the union of these sets, right? I was supposed to write them in a line like this to the left, but I don't have enough space. So I had to write one down. But I was supposed to put a union in between. So now, what does union tell us? The union tells us that you get to combine everything together. So if you look at the two diagrams, if you get to combine them, what region is going to remain unshaded? Is there any region that is going to remain unshaded, or the entire universal set is going to be shaded? Anyone? Anyone with an idea there? Or only A intersection B will remain unshaded? Are we all in agreement what he's saying? Have we paid much attention to the diagrams of what we have on top here? So that is basically true. So we have the left and the right hand side there shown. And we've seen that at the end of it all, they are all ending up to give us the same result. Are we together? Are we okay there? So now just a quick one to just show you how you get to confirm them instead of you proving them using the diagrams. In a case where we've given you a universal set, let this universal set of ours consist of members from 0 to 4. As simple as it is. Then we get to look at our A to consist members 0, 2, and 4. Then we also get to include our B with members 1, maybe let's say 1, and then we talk about 2. Then we exclude 3. 3 shouldn't be part of any set. Deliberately. So they ask you to confirm De Morgan's laws. I'm going to confirm one, then you can try out the other one. Okay, so we are saying A intersection B complement should be equivalent to what? To A complement union B complement. Are we together, guys? So now, I want you to approach these things the smart way. A intersection B, what does it mean? It means that you look at the elements that are common in A and B. That's simple. So let's look at our sets A and B. What elements are common there? Is there any other element that is common? Only 2, right? So you can put 2. So now, us saying that A intersection B complement is equivalent to 2 is wrong. So we are supposed to put what? I'll put a complement there. Okay. To show that we're interested in the outside that. Then our A complement is going to consist elements outside A. What are those elements outside A but within the universal? So remember, if you look at our A, we have 0, 2, and 4. So what elements are remaining in the universal set if we exclude 0, 2, and 4? 1, 3, right? So what is our A complement? Then our B complement is going to be what? The members outside 1 and 2? Okay, 0, 3, 4. Thank you. So now on the left part, when you say a complement of 2, it means you are only removing 2 from what? The universal set. What is going to remain, therefore? We are going to remain with 0, 1, 3, and 4. Then on the other part, you're looking at the union there. So the union of the two sets are going to be what? You combine all the elements together. So the list is 0, followed by 1, 3, and then 4. So everything that what we have is the same on the left and the right hand side. So now, there's one step that I actually skipped here. If you want to make even your work more easier, what you can do is, instead of you going so straightforward there, where you have your A, just put your A. So in your A you have 0, 2 and 4. Then you get to add a complement outside. Then again for the union, you show your union, then again you show your B, then put a complement outside of it. Of course it's still going to simplify to this and that. But all the same, it's still fine the same way we've done it. And you can make a statement. The left hand side is equivalent to the right hand side. Hence, confirmed. Or whatever they've asked you to do. So we've talked about De Morgan's laws. We also have what we call associative laws. So I like basically looking at associative to be something that deals with three things most of the times. Okay, so basically the very good idea of associativeness property, you look at addition. It basically gets to give you an idea. So think of three numbers. Let's say you have A, B and C as your numbers. So you adding A, you add it to, well, first of all you decide to add first of all B with C. Then you come and add it with A. Is the same as first of all adding A with B, then adding a C. Excuse us. Hello. Mioba, you're making noise with your friends, huh? Okay, so instead of muting you, we'll remove you next time. Kindly mute your mic. Thank you. Okay, so now, associativeness, we're looking at a case where you have three different numbers, okay? Now, what are we trying to say? Brackets from BODMAS, we are taught, get to start with what is what? What is in the brackets? That is a priority. So in a case where you have 2 being added to 3 plus 4, or maybe adding first of all 2 plus 3, then adding a 4. Do you guys agree that our result is going to be the same? And the difference is, you get to start with what is in the brackets. So here you have a 7. The other part you have a 5 plus 4. Are these not going to give us the same solution? So that property is what we call associativeness. So now we are looking at a single sign there. We only have addition, alright? We've only put addition there. So since we've only put addition, how can you think about it? You can now either put union and intersection to come up with the two associative laws. So in my first law I can start with my intersection, and then I'll tell you to say our associative law is basically A intersection B intersection C, then that is equivalent to A intersection B, again intersected with what? The C. Questions, yeah? Do you have questions? Okay, so you guys, how are you joining the class this time? Kawe, where were you? You've missed out a lot of things that we are trying to review. So this is our first associative law. For our second associative law, we have A union. We can just put a union instead. So we'll just B union C. Any questions there? So basically that's what we have. Associative laws are associated with, think of it in terms of addition. It doesn't matter what you get to start with, and that's what it implies when you say associative. So it's very easy for you to memorize them. Yeah, so understand them. Don't basically just master what, because think of it, in December you'll not be able to just memorize things because you'd have done a lot of content. So make sure you understand it. So you can also show these associative laws in the same way that I did show them the De Morgan's laws. So in terms of showing, you can start with the elements in A, Then you put a union as it is indicated there. Then you put the elements in B union C together. Then you put the elements in A union B together. Then you unionize it with your C. Then from there come up with your solutions. They should be the same. The same applies for the intersection. The most interesting ones, the ones that I like, distributive laws. So distributive is basically associated with multiplication, if you want to remember it. So for multiplication, we do understand that when you have A outside, B plus C, this is the same as what? A multiplied by B plus what? A multiplied by what? By your C. That is a basic distributive law. And if you understand that, you are home and dry. Okay, so now the basic sense, or something that we need to understand is, we need to understand that there is a multiplication sign there. And when you have A, B, it means that you are multiplying them, right? So it tells us to say that distributive, unlike addition, which is associative, we're going to talk about distributive law to be something that is going to involve both the intersection and the union. And in my first case, I can look at A intersection. So notice that we have two different signs. We have multiplication and addition. So I can have union inside there. So then we are kind of multiplying. So A intersection multiplied by B is going to be A intersection what? B. Again, the addition sign gets to go on the middle part there. So we have union. Then again we have A intersection B in the brackets. A intersection C, sorry. Okay. Then now the other part is going to be the opposite, where you get to put the union outside. Then inside you put the intersection. Like that. Then again, A multiplied by that is going to be A union B. Then again, intersection A union C. Questions there? Allow questions. Is it okay? Are we able to remember now the distributive laws? Or maybe you've not understood, I explain something that you need to get. Huh? I left. So I don't know how I accidentally left the meeting. So you're saying I repeat which parts? No, okay, so all these are distributive laws. Do I have to start from scratch? I'll repeat. I was saying distributive is associated with multiplication. Are we together? So when you have A outside, mute your mic, mute your mic. Okay. So when you have A multiplied by B plus C there in brackets, this is the same as AB plus what? AC. Implying that if you have a 2 outside and then you have 4 plus 6 in brackets, you can think about it in this way. You can also multiply 2 times 4, add it with 2 multiplied by 6. You're still going to have the same result there. So now what is the difference? The difference is on your left hand side, you start with what is in the brackets. So 4 plus 6 is 10. The other part, 2 times 4 is 8. 2 times 6 is 12. 20, 20. So this is what we're calling distributive law. Are we together? So now we are trying to apply this concept to intersection and what? And union. So now we can think of it in 2 ways. In the first part, we can put intersection where is our addition there. So I was saying for your own information, when you have something outside the brackets, what it means is what you're doing what? You're multiplying with what is inside. And when you have AB, it also means they are being multiplied together. Like that. So I was saying, if you have A intersection, then remember we have opposite signs there, so we can put a union inside. Then we can multiply by the A intersection. I'm trying to use the word multiply so that you get to remember. So A intersection multiplied by that is going to be A multiplied by our B. Then the sign in between, what is inside the brackets, is going to be there. Then again we multiply the A intersection by the C. It's going to be A intersection what? C. That is our first distributive law. The other one involves you having a union outside, then you have an intersection inside there. So basically what we have is we have A union B, then union, oh sorry, not union there. So there you need to have the sign in between there, so it is intersection. Then you have A union C, since we are multiplying there. So what I've done is I've multiplied this with a B, then I maintain the sign in between, then I multiply this again with a C. Any questions about that?
No.
There are no questions. Okay, so these are what you call the distributive laws. Okay, packed. Alright, so we've done the laws now. The common laws that we can get to meet. So just a few things that we need to understand, just a quick recap. When you have U minus A, any set being removed from the inverse set is the same as the complement of that set. An intersection of any set with the inverse set is what? An intersection of an empty set with any set is what? The union of an empty set with any set is what? The complement of the inverse set is what? The complement of an empty set is what? May I have solutions? Now we move. Any questions? If there are no questions, I need solutions to the questions that I have. So U intersection A is what? The inverse set intersected with any set is what? You guys, for how long have we been doing sets? Okay. Then intersection of an empty set with any set is what? Then the union of a set with an empty set is what? The complement of the inverse set is what? Then the complement of an empty set is what? Is there anything that you've not understood here? If you've understood everything, then we're okay. We are good to go. Okay. So buried. Let's try to talk about set interval notation, and I'm sure we can body this topic. Alright, so what is set interval notation? I've always said you can't understand set interval notation if you don't understand what real numbers are. And it's a case that most of us don't understand. I went as far as working on a video on that. I'm sure we've seen it. Some people are still behind. Is it a network? Are we all on the same page? Are we already able to see what I've put there? How many real numbers are between 1 and 2? How many real numbers are between 1 and 2? About what? You can't estimate approximately. Just try to estimate how many there. Okay, what is the smallest? Let's say we're moving from 1, right? We're moving from 1. What is the nearest number from 1 going this side? I want a very simple answer there. What would you think about if you're between 1 and 2? 1.1. Okay. Anyone with a different view? So somebody says they think the nearest number from 1 is 1.1. What if I talked about 1.01? Would you say it's after 1.1 or it's before? Okay. What if I talked about 1.001? Do these numbers exist, or I'm just imagining them? Somebody can continue adding zeros. So we can't tell which one is the smallest or the nearest real number after 1. It can be, of course, you may say, no, 1.0, but 1.0 is still 1 itself. So, yeah. So we don't know. So now this explains, I like some of the questions that I get to receive from students. They're like, okay, sir, you're talking about set A to have members between 2 and 4, right? But since you're saying 2 and 4 are not part of a set, why can't you just exclude them and include the exact elements that are part of a set itself? I don't know. Are you getting what I'm trying to say there? Why would you just show them if they're not part? We're not interested in them, but why are you showing them? Oh, so what I'm trying to say is, if you have 2 and 4 there, if you are able to tell a number that comes after 2, immediately the real number next to 2, if you're able to tell, let's assume if it was 2.01, and there, let's say our biggest number was 4.9, we would therefore these brackets would have not existed, okay? Would have just been using the same brackets, where we can say, okay, our A is just from 2.01 up to what? Up to, not 4.9, 3.9, sorry. So 3.9. Yeah, so that we are only showing what is part of the set. Why would we just show what is not part of the set? But it turns out to say we don't basically know the numbers that come immediately after 2 and immediately before 4. We don't know. So instead of us troubling ourselves, we can just say, okay, the real numbers that are in this set are basically between 2 and 4, where 2 and 4 are not part of the set. And that's why we have such brackets on top there. Okay, I hope that makes sense. So that tells us to say, when you have, okay, so this class for your own information, I'm approaching the class as a revision class to the people who've been learning already. Just a reminder, yeah, so we do have a class that is going to start from scratch, starting on Saturday. It will be a physical class. We are starting from step 1 in all the courses. So if you want to register, you can inbox or call the number that you saw on the flyer before joining the class. You can get in touch. And others who are up to date and would want to continue, we are starting functions as well. So you can join any of the classes in all the courses. Alright. Let's continue. So now, these brackets have got different meaning, of which I've already talked about these kind of brackets. Then for our set B, let's get to use different brackets there. Okay. Then for our set C, let's get to use different brackets as well. What if we get to use this one and that one, and if we get to combine them? So you can, it's not always supposed to be, they are not always supposed to match up. It doesn't mean that when 2 is part of the set, then even 4 should be part of it. No. So there may be a case where you're talking about set A to only consist of real numbers between 2 and 4, or where a case where 2 and 4 themselves are also part of the set, or where just 4 is part of the set, or where 2 is part of the set and 4 is not. Are we together? All those 4 cases are possible. Are we together? So now we need to understand how we get to show this on the number line. We get to show the curved brackets, okay, using what? So we'll draw something like that. Then I'll show the ending points. Then I can show we have our 2 and our 4. So that is okay for set A. Any questions? So we don't shade. When you don't shade inside there, it means that 2 and 4 are not part of the set. Only the numbers between 2 and 4 are part of what? Are part of the set. In a case where you get to talk about B, for B we are going to shade both ends, indicating that both 2 and 4 are part of what? Are part of the set. Then for set D, only one part will be shaded, implying that only 2 is part of what? The set. Are we okay there? Then for set C, only 4 is going to be part of the set. So that's very easy to follow. That's what they mean. Okay, just out of curiosity, let me ask you this question. Let's say you have set A consisting of elements 2, 4, 2, 3, 4. Okay, let me use just these elements to just see the way you guys are looking at this. Then I can also put set B. I can also put set C. Then for my set B, I can say we have 2 and 4. Like that. Then for my set C, I can say we have 2 and 4. So I want just to find A intersection B, A intersection C, and B intersection C. Very easy. So for A intersection B, what would you think? What do you think is the answer? A intersection B. Anyone to give us an answer there? 2 and 4. How are we going to present them? Using what kind of brackets? These or the parentheses there? What are we going to use? Yeah, they are very different actually. They are very different. We can see. So now, how are we going to present our answer? Or maybe you can give us any option. If you want, you can say there is no intersection. We'll still get your answer. Come on, guys. We're supposed to just. Mm-hmm. So you're saying this, right? Is that what you're saying? Are we all in agreement to what you say? With what? Also, you mean something like this? Is that what you're saying? Okay, are we now in agreement with the second solution that we have? Mm-hmm. So we use for A. Then what are the members? What are your solutions? What are your possible solutions? 2,4. Okay, are we now in agreement with the third solution, or we are still not okay? You have a different option? I'm not satisfied. I'm not satisfied. Anyone with a different attempt? I want to see the way you guys are looking at this. Come on, let's try to contribute. It's very interesting, actually. It's very interesting. You know, if you're able to answer these questions, then it basically gives me a picture to say that you've understood. Yes, we have an attempt from anyone. Only 4 will be part. Now, the brackets that we're going to use, I have noted this. Should I use the carry brackets? Okay. Alright, that's good. Do we have a different attempt? Different attempts? So it seems most of you guys have not understood. If not all, most of you have not understood. Um, okay. So the last one and the second from last us, right? Um, this one is not okay because you need to understand. I said if you look at 2 and 4, there are a lot of numbers in between. Now, if you look at the interpretation of the curly brackets, it means that you exactly this is what you call a finite set. Finite set. You basically understand and know the exact number of elements that are in such a set. You know that there are only 3 elements here. Now, for the set interval notation, you basically don't know. Right? You don't know how many members are there. There are a lot. So we are saying it's between 2 and 4, where 2 is also part of a set, but 4 is not. So there's no way 4 can be part of an intersection if it is not part of set P. So I like the approach of the last attempt there. Yeah. So 4 is not supposed to be part of an intersection. So the smaller set is A. So it is the one that is defining the kind of brackets that we're supposed to use. When for this, this doesn't exist. This 4 is not supposed to be part of a set. Then the last option is also wrong. Why do you think it is wrong? Anyone for an attempt now? What if I said 2 and 3 are part of the intersection? Would you argue? I'm asking you. If I said 2 and 3 were part of it. Okay, does that make sense to everyone? It's making sense now. Okay, so these are some of the things like when you understand concepts, you don't have to stick to the notes that you're given. Try to imagine and coordinate things. Try to see the way it is. So when you're talking about set interval notation, like I want to repeat, it basically it's an interval. That's why it's called set interval notation. It is not a finite set. You don't basically know the number of elements there, but all you know is it's a range. So if you had to say set B is from 2 to 4, it's something like that, right? So you have members from 2 all the way up to 4, but 4 is not. So, but we do understand that that thing that is in that set is also in between 2 and 4. So, in terms of our intersection, we can see that 2 and 3 are common because they are part of both A and B. 4 is not. So, if it was shaded there, even 4 would have been part of the solution because it is part of A and it would have also been part of B. But in this case, it is not. Does that make sense now? All right. Yes. Okay, so when you're looking at this, when you're looking at this set, the difference with if I was going to use that, the difference is here we have a lot of members. It's an interval. It's a range of real numbers between 2 and 3. Now this one is telling us to say that this set has only 2 members. That is a difference. Do you get the difference? One is showing us the exact members that are there. One is just giving us a range because it is not possible for you to list all the elements. That's why I was asking you to say how many numbers are between 2 and 4. You said there are a lot. So you can't list them. Are we together? So now, there's no way you can say all the elements between 2 and 3 are part of the intersection. It can't make sense. Why can't it make sense? Because A only has 2, 3, and 4. Meaning that the other real numbers that may be between 2 and 3 are not part of that set. Do we get the difference, sir? Okay, so you may not basically get to understand fully. So you're saying you've not gotten what I've said. I was explaining the meaning of the brackets. I was saying they indicate the members. So there's one that is giving us a range and one that is telling us the members. There's a difference here. So if you talk about set A, for example, you're able to show it in a diagram where you'd say you have 2 and 3. But in a case where you're talking about set interval notation, we use a number line because it's a range. Okay. So there are a lot, billions and billions of numbers between 2 and 3 for your own information. They're uncountable. So the difference is for these, we are looking at uncountable numbers. It's a range. Now for the curly brackets, we are showing the exact members that are there. That's the difference. So if you want to understand more basically, of course if you can't relate the two, you won't be able to understand just now. But I was just trying to give you an idea and try to think about it. You'll be able to understand with time. Okay. Let me just do one more example